All right, we are starting a new unit, and our new unit is applications of linear relations. So we just finished talking about linear relations, and now we're looking at applications, which, yes, is kind of like word problems, but don't worry, don't worry. They're not that bad. I hope that you're starting to feel confident with linear relations and the different ways that we express them or represent them. So again, we have talked about representing them um, in a table as a list of values, right? And looking for the pattern. We've talked about them as a rule or an equation written out. Sometimes we started describing them with words, sort of talking about the rule, right? Just describing the pattern, but then we looked at how to do it with an actual equation. Okay, and then the third one that we've looked at so far is with a graph, and you see a graph here. On the screen, one example of a graph. So those are the three ways we've looked at so far. And remember, what are those three most important, or sorry, the two most important properties or things to remember about a linear relation. And if you can remember that those are the two things you need to know about, then you're sort of halfway towards answering any question. And then it might be the case of, well, how do you find those two things? And then answer other questions from there. And we're going to continue to explore different ways that that same question is asked. Um, but you have to really remember it always comes down to those two things. And what are those two things? Well, they are where it begins or how much for zero and what is the change. And so we're not talking about the entire rule or the entire equation or the relation today. We're only talking about one part of it and how it relates to application. So we're going to focus on that. And just based on the title of this lesson, you might be able to guess which one of the two things we're going to talk about. Okay. But then starting tomorrow, we're going to connect what we're doing today to both of the properties of linear relations, both of those important things of a linear relation, and how the linear relations, how their applications work. And we're going to start looking at real applications of those. Okay. So the the title of this lesson is Rates of Change, and I hope you guessed that the between the two things, where it starts and what is the change, rates of change, what we're talking about today, has to do with the change in a graph. So we're not going to worry too much about where it starts today, although I am going to mention and point a couple of things out to start thinking about. But really today is about the change. And if before we get started, if you think about what an application is mathematics in mathematics is the same kind of computational or calculation math that we've been doing, but the change or where it starts or the equation for the rule or all those things, they actually represent something in the real world. That's the only thing that's different. All of the math is exactly the same. It's just that now it actually represents something. So that's a big part of what we're talking about today is what does it represent? How is it connected to the real world? So we're going to talk about some different rates of change and some different ways that different things that the change in a table or a graph or a rule that we were looking at in linear relations, how it's connected to the real world. And one that we look at, let's take a look at this graph before we get into it. This graph is a graph of distance and time. So if I look at, if I call this A, and I look at A, then I can see that they went 200 kilometers in what looks like 1, 2, 3, 4, 5, right? So we're counting by 1 hour here in 2 hours. 200 kilometers in 2 hours, or 300 kilometers in 3 hours, 400 kilometers in 4 hours, 500 kilometers in 5 hours. Okay. What does that mean? That is an average speed. That's what we're talking about. This is a car that is going the same speed over a certain amount of time. And in the first hour, the car went 100 kilometers. but after 2 hours, it went 200 kilometers, and after 4 hours, it went 400 kilometers, and so on, and it could keep going. So again, it's not about, well, it went 500 kilometers, period. It's how far did it go in a certain amount of time? And that is what we call a rate. Now, this is a nice rate to start with because it's one that we really understand very well. So average speed is how much, distance is covered in some amount of time. Okay? And that's what average speed is just in general. Now, what would be different units that we might have for average speed? So we kind of already saw this one, kilometers per hour. What's another one? Miles per hour. That's what they use in the States. Another common one in science class is meters per second. Okay, and again, a rate um, has two parts to it. So if I'm looking at a specific rate, like 200 kilometers in 2 hours, well, that's the same rate as 300 kilometers in 3 hours. So those numbers aren't the same, but the rates are the same, right? The change that's happening is the same. Of course, this looks like they've gone farther, but they've also spent more time driving or whatever it is, running, riding, whatever it is. In this case, I think probably driving. This one looks smaller, it looks shorter, but there's been less time that has passed. And so that's the thing about a rate is it can have different numbers, but the change is the same. The way it's changing is the same. Okay, and that's a big takeaway from today. Something that you want to think about over the next little while. In fact, whenever we're talking about what the rate of change or the change represents, that's what we're thinking about is what's the unit involved, or just what does it represent in the real world. Okay, so in this case, for this graph, our units are distance in kilometers and time in hours, and so that's kilometers per hour. That's a speed, that's the rate of change. Okay, calculate the average speed for each line. So I'm going to start with A. Now, how are we going to calculate these? Well, I can just start with one of these things that I have here, 200 kilometers in 2 hours. So I just divide 200 divided by 2, use my calculator. You might be able to do this one in your head. Gives you 100. So that's 100, and we'll include the units, kilometers per hour. 100 kilometers per hour, not just 100 kilometers, 100 kilometers each hour for 2 hours would be 200 kilometers. Again, I think this is stuff that you can follow, that you understand. But maybe we start to think about it in a different way when we're looking at thinking about it as a rate and how it applies to linear relations. Okay, let's do line B. So again, we can pick any one of these. I will pick this one here. Okay, so that's 400 kilometers in, following it down, that looks like 8 hours. So 400 divided by 8 is 50. Okay, and what if I had picked a different one? Would I get a different answer? Well, what if I do 300 kilometers in 6 hours? Let's try that one. I'm not going to write it down. 300 kilometers in 6 hours, still 50 kilometers an hour. And this is something that's going to be important. I'm going to talk about a lot of different important things, but if you don't remember them all, it's totally fine. because we're going to go back over all of them again and again and again. And like I've said before, when you start hearing the same thing over and over, it starts to stick, okay? So I picked this one and then I picked this one and I got the same rate. And that's because they're on the same straight line with each other. So they will have the same rate. That will always happen, okay? And that's going to be an important idea moving forward. So the last one, C, how about I pick this one, 100 kilometers in 4 hours is going to be 25 kilometers per hour. So what do you notice about those three lines and those three rates? We have talked about this before. At any point, if I ask a question and you want to think about it, go ahead and pause and just think about it. This is something, like I said, this is something we've talked about before. And A is the steepest line, and it's the fastest rate. B is the next steepest, and it's the next fastest. And C is the least steep line, and it is the slowest of the three rates. And that's not some kind of coincidence. That is the way this works, is that a steeper line means a faster rate or a larger rate. That's not always speed, so faster is not always the right word, but I think you get what I mean, okay? So what we've seen here is how to calculate the average speed. And notice that I didn't just leave it as a fraction that way. And when we did proportions, we talked about unit rates, and that's very similar to what we're doing now. If you remember that at all, if you don't, that's fine. But I've done the division, and even if it didn't work out and it gave me a decimal, I would still do it. I would still do this division and get this as an answer. And I've included units to think about what the rate represents. It represents the speed or kilometers per hour. Okay, 100 kilometers an hour, 50 kilometers per hour, and 25 kilometers per hour. Okay, determine the units for the rate in each graph below. Now, this is going to be important for us thinking about what the rate represents moving forward. And I think a lot of students struggle with it at first, but there's a really easy way to figure out what the units of the rate are for any question like this, okay? And remember, we talked about slope at the end of the last unit. And slope is another way of saying rate of change. So you might see slope a little bit here and there, but not very often. We're mostly going to talk about rate of change or change. But if you do see slope here or there, that's just what it means. So here's the trick about what you do. The units for the rate of change of the slope is always the units of the vertical axis over the units of the horizontal axis. So in this case, they are dollars per kilogram. And what is something that might be measured in dollars per kilogram? Maybe you can think of something. It might be something like gravel. Gravel could be dollars per kilogram, or like rocks or soil, dirt, right? Things like, even if you're shopping at a bulk store or in a bulk place, then that's measured in weight, and you pay a certain amount per how much weight you've got. Okay, and so those are some examples of something that might be dollars per kilogram. And so let's say you're buying some candy, and for 0 kilograms, you might pay $0, but for 1 kilogram, 2 kilograms, 3 kilograms, you're going to pay more. Okay, and that's going to form a straight line, and the rate of that would be dollars per kilogram. Second one, temperature over time. And so the units of the slope are going to be degrees Celsius per hour. And that might be my coffee, after I make it, starts nice and hot, and every hour it cools off, right? And that might be something like that. So, or it could also certainly start and go up. It certainly could do that as well. But I'm just giving an example of one that is going down, that's decreasing every time or getting smaller. Um, and every hour the temperature drops, or every hour the temperature rises, right? So that's degrees Celsius per hour. And so notice that all I ever do is take that unit over that unit. That's how you do it, okay? So that can help me think, if I can figure out what the units are, now I can think, what does that mean? And that means the change in temperature over time, right? That's what the rate represents. It represents the change in temperature over time, okay? So a lot of what we're going to have to do is, it's going to help you to solve problems to think about the units of the rate of change in the applications that we're going to look at. Okay, we're going to look at a few more examples. You can go ahead and, again, pause the video if you want and go ahead and try to find these rates if you think you can do it. Whoop, looks like A is missing here, so I'm going to add that in. That's obviously A, and then B and C are there. Calculate the rate of change for each of the lines and include units. What does the rate of change represent? So, earnings per hour, right? That's what this one is talking about. So for A, I'm going to pick a value here, and it's only got 1 point on it. Now, I don't have to use points that I'm given. We'll see this in other examples going forward. I could use any point on the line that's a nice point. I wouldn't use some point in here because I would have to guess at exactly what, let's say, this point is. And I might be right in some cases, but it's not a good idea. So I want to use perfect points. And in this case, I'm given perfect points, so why not use that one? Okay. So this is $150. This person earned $150, right? This is what this point means. In how many hours is that? 1, 2, 3, 4, 5. So that's 2 hours. So in 2 hours, and on my calculator, I'm going to go 150 divided by 2, and that's 75. And I'm supposed to include units, so that's dollars per hour. Okay. Now, what about B? Don't write anything down. I just want you to watch for a minute. Okay. If you're copying this down, just stop writing because I want to try something here. What if I pick this point? Okay, this point looks like 50, 60, 70, 80 in 2 hours, which is 40. That would be dollars per hour. What if I pick this point? This point looks like 100 in 4 hours, which is $25 per hour. Well, hold on. I told you that when points are on the same line, the rate will be the same. Why am I getting two different rates? This person is making the same amount every hour. Take a look at when I look at like that. They're making $10 every hour. $10. Let me do this in a way that you're going to see it even better. Okay, so we're starting here and we're going $10 in 1 hour. 10 more dollars in 1 more hour. 10 more dollars in 1 more hour. 10 more dollars in 1 more hour. Okay, because my change every time is 10. I'm going up 10 in 1 hour. Okay, so why did these two questions give me a different answer, and neither of them is 10? So this is the last trick from today that you really have to remember, and as we work through this, trust me, you will. It may seem strange at first, but you will definitely get the hang of this. And it's because this one doesn't start at 0, right? And so the way that I'm calculating it doesn't make sense if I'm not starting at 0. And let me show you exactly what I mean by that. To accurately calculate B, I could just do it from the graph like I did, or I could use 2 points, okay? And I could look at the change between those 2 points. Between those 2 points, I went up 20, and I went over 2. So I earned $20 in 2 hours, and $20 in 2 hours is $10 an hour. And I can do that because the scale is nice. But the other way I could do this is I could look at this one as 100. This one is 80. So I'm going to subtract 80 to find the change there. And this one is 4. And this one is 2. So 4 minus 2 to find the change there. 100 minus 80 is 20. 4 minus 2 is 2. That works out to 10 over 1, or even better, 20 divided by 2 is 10. And I'm going to add the units back in, dollars per hour. So we're going to talk about this more. This is like a little formula. We are going to talk about it more. Okay, if you already understand that, great. You can go ahead and use that. If you're like, if that was a bit of a leap for you and like, whoa, what happened there? Just let me show you again, because you probably followed it fine when I did it on the graph. And when I go from this point to this point, I am going from 80 to 100. 80 to 100, which is a change of up 20. Every one of these is 10, 10, 20, 30, 40, 50, right? So going up 2 is going up 20. Then I went from 2 to 4. From 2 to 4, each one of these is 1, 1, 2. So that's plus 2. So that was $20 in 2 hours. And that's why this works. Think about what we did before. We said this was 80 in 2 hours. But that's not exactly what happened, because they started at 60. For whatever reason, this is like, let's say this is a plumber who charges, or an electrician who charges $60 just to show up at your door. This is how this often works. It's $60 to start, and then $20 each hour after that, or $10 each hour after that. It's pretty cheap for an electrician. I don't know any that work that cheap anymore, right? But that's how their cost structure works. $60 to start, and then $10 per hour after that, okay? Because it costs the money just to drive to your house and to drive away from your house. So they charge more just to show up at your door. That's part of the reason why that happens. Okay, there are other reasons as well. But that's why this is actually $10 per hour. It's actually, again, $20 in 2 hours, just like this one was $20 in 2 hours, because I started at 60. So when I don't start at 0, I can't just do it like I did for A. I actually have to use 2 points and look for the change. And in fact, when I'm doing A, I'm using this point and I'm using that point. And what I'm actually doing is 150 minus 0 over 2 minus 0, which is 150 over 2, which is $75 per hour, right? That's what I'm actually doing when I'm sort of cheating. And if a line goes through the origin, through 0 like that, I can cheat and I can just use a single value. But if the line doesn't go through the origin, I can't cheat, and I need to use 2 values to figure out what my change is. Okay, so that's a big takeaway from today. Let's finish the last one, C. I'm going to do it both ways to show you that the way we did B will always work. But if you know when you're allowed to cheat and you want to use that shortcut, by all means, you're allowed to do that. So this point is 80 in 4 hours. Okay, and this point is 40, let me write that down, in 2 hours. So my change is from 40 up to 80, which is 80 minus 40, over from 2 to 4. So that changes 4 minus 2. 80 minus 40 is 40. 4 minus 2 is 2. 40 divided by 2 is $20 per hour. Okay. And let me see. Okay, so let me get rid of that. I hope you followed that okay. That was using both points. What if I just used one of them? $80 in 4 hours would be 80 divided by 4, which is 20 again, dollars per hour. So this worked because C also goes through 0, 0. That worked fine. But only when a line goes through 0, 0 can you do that. It doesn't work for B. If you remember when we did B, you can go back in the video and watch. We tried it with these points and we got two different answers. But I hope I've convinced you that 10 is the correct answer. Okay. Now, take a look again. B is higher than C, but it's a lower hourly rate. Why is it higher? Well, because they started higher. But you can see that it's slanted more, and if I extend it, C is going to eventually overtake it, right? And earning $20 an hour in the long run is going to be better than earning a little bit up front, but only earning $10 an hour. That's something we're going to talk. Don't worry about that right now, but it's something we're going to talk a lot about. And I think it's helpful to think about that when we're thinking about these representations and these lines and all of that stuff. Okay. Now, what does the rate of change represent? The rate of change represents, sometimes you can kind of describe it with words. Sometimes you can't, and that becomes difficult. But the rate of change represents, in this case, your hourly wage. This is tricky. I'm not going to get into it too much right now. Um, It's tricky because people will say how much they make. Well, that's not true because the rate of change isn't how much they make. That's the total amount that they make. That depends on how long they worked, depends on their hourly wage, but also depends on if they got any money up front, like the person in B did. The rate of change is just the part that's changing. And in this case, it's the hourly wage. What we're going to call that starting amount is going to be the fixed amount or the starting amount or the initial amount. And the total has to do with both. It has to do with the initial amount, what the hourly or the rate is, and how long you've been working for or whatever it is, right? All those factor into how much total money you're going to have. So if we're asked for what does the rate of change represent, we're just looking for that. But sometimes there's not a good way of explaining it with words, and so we have to, we're going to explain it in a different way, and it's not going to be super sophisticated, so don't worry too much about that right now. Okay, B is, we've kind of seen this before, it's distance and time, and distance is in kilometers and time is in hours. So again, my units are going to be kilometers per hour. Okay, it's always this one over this one. Don't do it backwards. Don't do hours per kilometer. Okay, and so we've already seen this. This is like an average speed. It doesn't start at 0. It ends at 0. That doesn't matter. It doesn't start at 0. So I have to use 2 points. So you can pick any 2 points. I'll pick this one and this one. And if you pick 2 different points, that would be great. And let's see if we get the same answer. So this is, let's see, we're counting by tens. So 120 at, looks like 1 hour. And this looks like 30 in 4 hours. Okay, so my rate is 120 minus 30 over 1 minus 4. Now, some people might have put 4 minus 1 on the bottom. Why did I put 1 minus 4? Because the 120 goes with the 1, so I have to start with both of those. Okay, 120 minus 30 is 90. 1 minus 4 is negative 3. 90 divided by negative 3, use your calculator, that works out to negative 30. What is going on with that negative? Well, you probably have already figured out it's because that line is going down. So it makes sense that that is negative. I'll add in the units here, kilometers per hour. So the rate is average speed, or just speed would be fine. Okay, and in this case, their speed is going in reverse. Okay, or they're going towards their home instead of away from their home, or whatever the situation is. Okay, let's say I had done it the other way. Let's say I had started with 30 because it's the point that's over here. Whoops. Let me add these back in. Well, then I would have got 30 minus 120 over, again, because I'm starting with 30 now, I got to start with the 4. 4 minus 1, which would be negative 90 over 3, which is still negative 30. So as long as the same ones go together, okay, 30 was in 4 hours. I was at 30 after 4 hours. It's important that those go together. And in that case, if I do it correctly that way, I will get the same answer. Doesn't matter which one I start with, okay? But what you wouldn't be able to do in a case like this is 120 minus 30 over 4 minus 1, because that would give you positive 30, and that is incorrect. And we can see that this has a negative slope and it's going down. So there's a lot of things that go into that, and a lot of different ways that I can hopefully understand the same thing, okay? Okay, let's try. I think there's one more here. There's 3 again, so you can go ahead and start. All of them go through 0, 0, so we can cheat with all of them. But what's different about this one is there are no nice numbers. Or there are nice numbers, but it doesn't give them to us. It doesn't give us those points. Okay, so I'm going to start with A here. And for A, I'm going to pick 2 points because A has lots of nice points. You don't have to. I'm just doing it to sort of, again, prove that this works. So I'm going to pick that one and that one, and just for us to get used to it. So from 50 to 150 is a change of 100, because that's 150 minus 50 over, that looks like 3 minus 1. So 150 over 50 is 100. 3 minus 1 is 2. 150 divided by 2 is 50. And that's apples per box. Okay. Let's see. So again, I did 150 minus 50, showing the change from 50 to 100 was plus 100. And from 3 minus 1, showing the change from 1 to 3, which is plus 2. And 100 in 2 is like 100 divided by 2, which is 50. I could have also just used this, which was 50 in 1, because it goes through 0, and that would give me the same thing, 50 in 1. What about B? Okay, follow along and find whatever point you want. How about this one? That looks like 50, 60, 70, 80, 90. And that looks like 1, 2, 3, which is 30 apples per box. And for C, how about we make our life easy and we just use the first point that we can come across. That's 10 and that's 2. So that's 10 in 2, which is 5 apples per box. Now that's a strange, unit for rate. Why would you have different numbers of apples per box? Well, I mean, you might buy the 50 apples per box if you are making pies, or you are a store that's selling apples or something like that. You might do 30 apples per box if you're just making a bunch of pies for a farmer's market or for a family get together. And you might buy the 5 apples per box if it's just for your home. And if I buy 2 boxes, then I'm going to get 10 apples, which is what the whole rate thing means, right? 5 apples in each box, 2 boxes means I get 10 apples total, okay? Now, what does this represent? The rate represents the number of apples in each box, okay? Don't say the number of apples in one box or the number of apples in a box, because that's not necessarily quite right, and I don't want to get into it too much, but we'll talk about it more later. But it's in each box, okay? Or number of apples per box is another good way of saying it. Okay, these are the two ways that I want you to try to describe the rate of change, or when it says what does the rate of change represent, the number of apples in each box or the number of apples per box. That's how I want you to say it. Don't say in one, or don't just say the number of apples, because that's not correct either. Okay, okay, I hope that's okay. We've got one more little example here that we're going to go through. And again, this isn't something that we're going to do a lot of yet, but it comes back to that idea of sort of cheating or not cheating, okay? And I'm going to show you this now, and we're going to come back and look at more examples like this in the future. But for some of you, you're going to connect to this and you're going to get it. After working for 5 hours, Bill had made $110. After working for 20 hours, Bill had made $335. Calculate the rate of change in this situation. What does the rate of change represent? So if he made, so let's see. Okay, I'm just going to do some thinking over here. I'm going to play around a little bit. If he made $110 in 5 hours, what does that work out to? $22 per hour. Then it says he made 335 in 20 hours. 335 divided by 20. 1675. What's happening here? Why are they different? Is it because they're different jobs and his hourly rate changed? It is not because of that, okay? It's because that's not the only thing that's factoring into how much money he's making. So this is one of those cases where that's not what his hourly wage means, okay? So he earned $110 in 5 hours and $335 in 20 hours. Well, hold on. Let's do it this way. 335 minus 110 over 20 minus 5. 335 minus 110 is 225. So I know for sure that in those extra 15 hours, the change from 110 to 335 is 225. And then from 5 hours to 20 hours is 15 hours. So now if I do 225 divided by 15, and I get $15 per hour, that's the actual hourly wage. This is one of those situations where Bill started up here and went up. And so just doing it like this didn't give me the right answer, because there's another amount of money involved in the question. Again, don't worry too much if you don't think you can do this yet. It's not a big part of what we're doing today, but it's what we're going to work towards down the road. Okay? And by the time we get there, you'll have a lot of experience working with these, and it'll stick a lot better. But the point is, you have to be careful about just taking one single amount and doing the dividing, because it may not give you the right answer. And when it's given in words like this, I don't know if it has a starting value or not. Now, when I look at the graph, I do know that. When I look at this graph, I know A and C, I can cheat, and B, I can't. Okay? But this is just, again, another reminder of being careful that sometimes you can't just divide directly. You got to do a bit more work. Now, how could we find the initial amount if we wanted to? Well, that's something that we'll save for another day, but it is something that we're going to work towards being able to do. Okay, so good luck with all of this. Rates of change, what do they represent? What are the units? And how do we find them? And specifically, we were doing it from a graph today. Those are the big takeaways from today, the big things you want to be thinking about. Again, if you feel like you're not quite there, that's okay. We're going to do a lot of this. But keep those three most important things in mind. What are the units? What does it represent? And how do we calculate it given those values in a graph or something like that.